So picture this. Right now, as we're recording, 4 humans are hurtling toward Earth at 24,000 miles per hour inside a capsule that's about to hit the atmosphere like a meteor.
Artemis 2, the splashdown's happening today, isn't it?
Within the hour, Pacific Ocean off San Diego. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen from the Canadian Space Agency. First crewed lunar flyby since Apollo 17 in 1972.
That's 54 years.
54 years, and here's the number that caught my attention. They just traveled 252,756 miles from Earth. That's a new record, beating Apollo 13 by over 4,000 miles.
Furthest any human has ever been from the planet.
Right, and the reason we're talking about this on Auto Intelligence isn't because it's space news. It's because the technologies required to move humans and cargo on the moon are the same technologies transforming mobility on Earth.
Battery thermal management, autonomous navigation, energy logistics, supply chain architecture.
Exactly. This is convergent engineering, and it's happening right now.
Auto Intelligence is produced by Auto Agentic. I'm here with my co-host, and today we're diving into something that might seem off-topic at first glance, but is actually deeply relevant to anyone thinking about the future of mobility systems.
Whether you're starting your day or catching up later, let's get into it.
So Artemis, where do we even start with this?
Well, let's start with what Artemis 2 actually accomplished. This wasn't a landing mission. It was a validation flight. The crew tested deep space navigation, life support, communication systems, all the foundational tech for what comes next.
Which is what exactly? The program's been restructured, right?
Yeah, and this is where it gets interesting. Artemis 3 was supposed to be the first crewed lunar landing. That's now pushed to Artemis 4 in early 2028.
What happened?
NASA restructured in late February. Artemis 3 is now an Earth orbit mission where astronauts will test docking with the lunar landers, SpaceX Starship, and potentially Blue Origin's Blue Moon. They'll validate propulsion, life support, and the new spacesuits.
So they're de-risking the landing by testing everything in low Earth orbit first?
Exactly. And then there's the bigger strategic shift. On March 24th, NASA canceled the Lunar Gateway.
The orbital station?
Right. They're redirecting $20 billion toward a permanent lunar surface base instead. 7-year build timeline. The rationale is twofold. Accelerate surface operations and compete with China's International Lunar Research Station, which is targeting a basic model by 2035.
That's a pretty fundamental architecture decision.
It is, and here's the crossover. This mirrors what we're seeing in terrestrial mobility. The economics favor distributed surface infrastructure over centralized orbital platforms.
Like distributed charging networks versus centralized refueling depots.
Exactly. The same economic logic applies. You want infrastructure where the operations happen, not an intermediate step that adds complexity and cost.
That's a pretty direct parallel.
So let's walk through the mobility stack, because every layer of this program has a terrestrial equivalent. Start with Earth to orbit. How do you actually get stuff to the moon?
SLS, right? Space Launch System, that's the big NASA rocket.
Yeah, Boeing builds the core stage. Northrop Grumman does the solid rocket boosters. Each launch costs about $4 billion.
$4 billion per launch?
Per launch. And SLS development alone has exceeded $23 billion against a 2011 estimate of $10 billion. So, not exactly a model of cost efficiency.
And it's not reusable.
Limited reusability. NASA's trying to transition operations to a commercial consortium called Deep Space Transport, Boeing, and Northrop Grumman to eventually reduce costs. But the pathway's unclear.
So you've got this legacy architecture that's expensive and not particularly scalable.
Right, and then you've got SpaceX Starship on the other side, which is the designated lunar lander. Fully reusable in theory, but there's a bottleneck.
Orbital refueling.
Orbital refueling. A single Starship lunar mission requires approximately 10 tanker launches to fuel one lander. You're launching propellant into orbit, docking, transferring fuel, repeating. It's a massive logistics operation.
And that hasn't been demonstrated yet?
Not at scale. SpaceX has completed 49 development milestones, but the ship-to-ship propellant transfer demo is scheduled for this year, 2026. It requires 2 Starship launches spaced weeks apart, orbital docking, fuel transfer, significant thermal engineering to prevent boil-off.
This is basically the space equivalent of depot charging infrastructure for EV fleets.
That's exactly what it is. You're solving energy logistics. How do you stage, store, and transfer energy at scale to enable mobility? The tanker-to-depot model maps directly to grid-to-fleet energy distribution.
Same problem, different environment.
Now, surface mobility. This is where the automotive crossover gets really direct. The lunar terrain vehicle.
The rover?
The rover. $4.6 billion contract over 10 years. 3 companies competing. Intuitive Machines, Lunar Outpost with GM, and Venturi Astrolab. NASA's about to down-select.
And GM's involvement here is battery systems.
Battery systems and drivetrain. They're using lithium-ion cells with NCMA cathode chemistry. Nickel, cobalt, manganese, aluminum.
Wait, NCMA, that's the same chemistry in the Hummer EV and Equinox EV, isn't it?
Same chemistry, same platform. GM has explicitly stated that the engineering work on the lunar rover battery will directly advance their terrestrial EV technology.
So this is dual-use R&D?
Exactly. And the engineering challenges are extreme. The rover has to survive lunar night at minus 280 degrees Fahrenheit and daytime peaks of 260 degrees.
That's a 540-degree temperature delta.
540 degrees. And the battery has to keep working. You need fault tolerance so the system continues operating with failed cells, active heating elements for night survival, extensive thermal insulation.
And all of that engineering, solving for extreme cold performance, thermal cycling, safety margins, that feeds directly back into improving cold weather EV performance on Earth.
Right. This is the clearest technology transfer in the entire program. You're stress testing battery systems under conditions that make a Minnesota winter look mild. The insights transfer.
What's the design spec for the LTV?
Carry 2 astronauts in spacesuits plus 500 kilograms of cargo. Design lifetime, 1 decade. Range target, up to 19,000 miles.
19,000 miles on the moon?
Nearly 1,000 times the distance traveled by Apollo-era rovers. This isn't a short-term exploration tool. It's infrastructure.
Before we go further, this episode is produced by the team at AutoAgentic. They're focused on building the intelligence layer for the automotive industry, helping organizations move beyond disconnected tools toward more coordinated thinking around how data, workflows, and AI come together. As the industry explores how to operationalize these systems, companies like AutoAgentic are working alongside dealerships, dealer groups, and OEMs to understand what it takes to make them function in real environments. If you're interested, visit autoagentic.ai.
Let's talk about autonomy, because this is where lunar and terrestrial mobility challenges become almost indistinguishable.
You're thinking about Viper?
Viper's a good starting point. Volatile's investigating polar exploration rover. Golf cart-sized autonomous robot designed to prospect for water ice in permanently shadowed craters at the lunar South Pole.
Some of the coldest locations in the solar system, right?
Right, and it has to navigate autonomously. No GPS, no real-time control from Earth because of communication lag. It uses onboard instruments. Neutron spectrometer for subsurface water detection, a 1-meter drill for sample extraction, spectrometers for analysis.
So it's autonomous resource extraction.
Autonomous resource extraction in an environment with zero infrastructure. And then there's Cadre.
What's Cadre?
Cooperative Autonomous Distributed Robotic Exploration. 3 shoebox-sized rovers that autonomously navigate and create cooperative 3D maps. Multi-agent coordination.
Which is the same problem autonomous vehicle fleets face on Earth.
Same problem. Cooperative path planning, precision localization without GPS. Real-time environmental mapping. The algorithms being validated on the moon will feed directly into terrestrial autonomous systems.
And they're building lunar navigation infrastructure too, aren't they?
Yeah, Lunar Node 1. It's a radio beacon network that provides geolocation for landers, rovers, surface infrastructure, astronauts. Think of it as lunar GPS.
So you're architecting the same navigation stack that autonomous systems need on Earth, just on the moon first.
Right, and there's something interesting about that sequencing. Solving these problems in the most extreme environment forces you to build systems that are robust, fault-tolerant, and genuinely autonomous. You can't rely on connectivity. You can't rely on human intervention.
The constraints force better engineering.
The constraints force better engineering. And then that engineering transfers to less constrained environments and just works better.
What about the spacesuits? I saw something about those being redesigned.
The AXIMU, Axiom Extravehicular Mobility Unit. This is actually a really interesting piece of wearable mobility engineering.
Wearable mobility?
Think about it. A spacesuit is a one-person vehicle. It has power, thermal management, communications, navigation, life support, all integrated into a wearable platform.
I hadn't thought of it that way.
The Apollo suits were essentially inflated balloons. They severely limited motion. The Axim-U uses flexible joints. Astronauts can kneel, jog, perform splits, over 850 hours of pressurized testing.
And the design accommodates?
At least 90% of the U.S. male and female population. 4G communications, Prada-designed thermal layers, interestingly, Oakley visor optics.
So the human-machine interface engineering here, where else does that apply?
Exoskeletons, industrial wearables, advanced protective systems for cycling, motorsport, any domain where the operator is the vehicle. The principles transfer.
That's a fairly broad application space.
Now, supply chain, this is where the program gets really interesting from an infrastructure perspective.
In situ resource utilization, ISRU.
Right. The capability to extract and process resources at the destination rather than transporting everything from Earth. For the moon, that's primarily water ice.
Which you can split into hydrogen and oxygen for propellant.
For propellant, life support, industrial processes. You're essentially building a local supply chain on the moon.
What's the timeline for that?
Resource mapping completes between 2026 and 2030 through orbital surveys and missions like Viper for ground truth. ISRU demonstration projects run 2030 to 2032 for small-scale processing validation.
But there's uncertainty in the resource characterization, right?
Significant uncertainty. Current water content estimates are from indirect measurements. Concentration, depth, purity, regolith mechanical properties, all of that remains poorly constrained until surface missions deliver actual data.
So you're building an extraction infrastructure for a resource you haven't fully characterized yet.
You're building the capability in parallel with characterization, which is, well, it's a risk, but it's also how you move faster.
And the economic logic here is what? Reduce transport dependency.
Reduce transport dependency, build resilience, lower unit costs at scale. It's the same logic driving nearshoring and localized production in terrestrial manufacturing.
ISRU is just supply chain transformation.
ISRU is supply chain transformation. You're shifting from a centralized Earth export model to distributed local manufacturing. The principles are identical. And then there's the competitive dimension, because this isn't happening in a vacuum.
China.
Chang'e 7 launches this year for South Pole resource exploration. Chang'e 8 in 2028 to validate ISRU. The International Lunar Research Station with Russia targets initial elements by 2028 and a basic model by 2035.
And China's aiming to land astronauts on the moon by
2030. So NASA's gateway cancellation and the pivot to a surface base are explicitly framed as competitive responses.
This is infrastructure competition.
The race isn't to visit the moon. It's to establish permanent infrastructure that enables sustained operations, resource extraction, eventually industrial presence.
And whoever builds the supply chain and mobility infrastructure first
establishes the operating framework for decades of lunar activity.
Which is the same competitive dynamic playing out with EV infrastructure on Earth.
Exactly. The regions and companies that build charging networks, battery supply chains, autonomous vehicle frameworks first, they capture long-term market position. This is infrastructure layer competition. Same structure, different location.
And the technologies are converging because the fundamental challenges are the same.
The fundamental challenges are the same. Energy logistics, autonomous navigation, thermal management, supply chain architecture, you're solving mobility problems. The environment changes, but the engineering domains overlap. So, what do we take away from all this?
Well, I think the first thing is just recognizing that this convergence is real. It's not metaphorical. GM is literally using the same battery chemistry in a lunar rover and a consumer EV.
Right, and the engineering insights flow both directions. Solving for extreme conditions on the moon produces technology that improves performance on Earth.
The other thing that strikes me is how much of this is about infrastructure, not just vehicles. The orbital refueling architecture, the navigation network, the SRU supply chain, the surface base.
You can't have sustained mobility without infrastructure, on the moon or on Earth.
And the competitive dynamic is about who builds that infrastructure first and sets the standard.
Which has pretty direct implications for how we think about terrestrial mobility infrastructure investment. The decisions being made now about charging networks, energy distribution, autonomous navigation systems, those are foundational.
They define the operating environment for decades.
Right, and I think there's something else here too. The way NASA restructured the program, canceling Gateway, moving to a surface base, testing systems in Earth orbit before committing to lunar operations.
Pragmatic risk management.
Pragmatic risk management. They're prioritizing what actually enables sustained operations over what's symbolically impressive. That's a useful frame for thinking about any infrastructure investment.
Build what works, test before you commit, focus on the economics.
Focus on the economics, which brings us back to the question of whether this is sustainable. $31.6 billion spent so far. $4 billion per SLS launch. The cost structure's challenging.
But the shift toward commercial operations, the CLPS program, the competitive LTV contract, those are all moves toward a more sustainable model.
Potentially. If the technology transfers deliver value and if the infrastructure enables economic activity beyond exploration.
Which depends on ISRU working.
Which depends on ISRU working, and on orbital refueling working, and on the LTV lasting a decade in that environment, and on... There are a lot of dependencies.
There are a lot of dependencies, but that's true of any infrastructure build-out. You're making bets on future capability.
You are, and what's interesting is watching those bets play out in parallel, on the moon and on Earth. Same technologies, same challenges, same competitive dynamics.
Same fundamental question. Can you build mobility infrastructure that's economically sustainable at scale?
Can you build mobility infrastructure that's economically sustainable at scale? That's the question. So, Artemis 2 splashes down today. 4 humans just completed the furthest journey from Earth in history, and the technologies that got them there and will eventually enable sustained lunar operations are the same technologies reshaping how we move people and goods on Earth.
Battery systems, autonomous navigation, energy logistics, supply chain architecture.
Convergent engineering. And we're watching it happen in real time.
The next few years are going to be fascinating. Artemis 3 in 2027, the LTV contract decision, SpaceX demonstrating orbital refueling, Viper landing, Chang'e missions. The infrastructure race is accelerating.
And the implications extend well beyond space exploration. This is about who defines the operating framework for extreme condition mobility technology.
Which feeds back into terrestrial systems. This episode was produced by the team at AutoAgentic. As the automotive industry continues to explore how AI and integrated systems can improve operations, AutoAgentic is working with dealerships, dealer groups, and OEMs to better understand what it takes to make these technologies function in real-world environments. They're focused on building coordination between data, workflows, and intelligence systems, helping organizations move beyond isolated tools toward more connected operational thinking. If you're interested in learning more, visit autoagentic.ai.
And as always, we'd love to hear from you. Your perspectives, your experiences, the questions you think the industry should be asking. Reach out to Barry at autoagentic.ai.
New episodes every Tuesday.
Thanks for listening.